welcome to lecture 21, and we are now in a position to do various things. After we have learned how to tackle differential equations, some interesting circuit problems we can do. Let us in the form of some examples, numerical examples, let us highlight how to apply those techniques that we have learned to solve differential equations, direct applications. Let us see. Suppose we have told about earlier that you can charge a capacitor by having RC circuit and things like that, and we have so far considered in the circuit there is only one energy storing elements are present. Now, let us do something interesting now. For example, you have got an inductor here and a capacitor. Okay. Sorry, and a capacitor. And there is no source, and there is a switch here. Now, the question is, if you close the switch at t equal to 0, will there be any current? Yes, there may be a current provided this capacitor had some initial voltage already charged from some other circuit, and we have done this problem, that is a charged capacitor, and we dissipated the energy in a resistance. Earlier we have done RC, a charged capacitor was initially charged with a voltage V naught, and then we did like this. Now, suppose I say that I put some number L equal to 2 Henry, and C is also 2 farad. Mind you, these numbers 2 Henry, 2 farads are too large. I mean 2 Henry inductance is very large inductance. Similarly, 2 farad capacitor is very large. To keep our computation simple, and I have chosen these values. They may not be this L with 2 Henry, C with 2 farad will not be easily available. But anyway, to give you the idea what is the problem, I am telling you that the voltage across the capacitor I will denote it by V, because V may be time varying, with the condition that V 0 minus was equal to some 10 volts, say, initial condition. Similarly, I have to specify, because inductor is an energy storing element, I must specify also I 0 minus. Suppose it is 0. Okay. Now, I will close this switch at t equal to 0. From there, I will start counting my time and want to find out the currents in the circuit. That is the problem, statement of the problem. So, initially charged capacitor with 10 volt with this polarity plus minus, close the switch, and I want to solve for the current I t. Okay. Therefore, at t less than 0 circuit was open, there was no current. So, that was fine. Now, for t greater than 0, say equal to 0, the circuit is like this, L, that is 2 Henry, and circuit is closed. (2 farad), and let us assume the current in the circuit to be I t at any time t. Direction of I t is my choice, I have assumed it like this, and this was the voltage across the capacitor plate. And what will be the voltage across the inductance? Once you have assumed this will be L d I dt, is not? This will be the thing. Then I write down the KVL equation in this loop. So, start from this point, from this to this plus V, then from this to this minus L d I dt, and that is equal to no other voltage, that must be equal to 0. No external source is present. So, I have taken everything here, that is fine. Now, coming to the capacitor, once again you see, look at the capacitor separately. What I have done, this is the polarity of the voltage I have shown, and this is the current I have shown, I t, is not? What this capacitor? This is I t. I can say that minus I t this way. Therefore, that C dV dt, then I should write it as minus I for this problem. This point is crucial, students often mistake here, because you must always remember, if you have assumed current this way, voltage across the inductor is L d I dt. Okay. If it is a capacitor, see, if current enters through this terminal, where I have also assumed voltage polarity to be like this, then I will say I is equal to C dV dt. But here I have assumed I t like that. Fine, L d I dt, no problem. In the capacitor, the current is leaving plus terminal. That means minus I is entering through the plus. So, it is the minus I which should be equal to C dV dt to be consistent with this. So, these two things you must always remember. Similarly, for resistance, of course, it is like this, plus minus R I. This is a very important step. Now, then this is the thing. So, my first goal, and suppose I want to know the voltage across the capacitor at any time t, V t is how much, and also current in the circuit at any time t. Current will be same because they get series connected L C, it cannot be different. Now, so these are the two equations. Therefore, my first task is to trying to solve for V, trying to solve for capacitor voltage, capacitor voltage V t at any time t, what is the capacitor voltage. Therefore, my target will be to form a differential equation involving V only. I will not form any integral differential equation. So, from this equation I will write V minus L and d dt into I, this I, and I is minus C dV dt, which means that I is equal to minus C dV dt. So, put it here minus C dV dt, and that is equal to how much? 0, because no external voltage, forcing function is 0. The initial energy stored in the capacitor will drive the circuit, we will see. So, this is the thing. or I will say this equation is nothing but LC d2v dt2, this will become plus v is equal to 0. And this one I have learned how to solve differential equation. I will make this coefficient of this highest derivative term, that is d2v dt2 here 1. So, divide by LC on both the sides, 1 by LC into v is equal to 0. This will be the thing. And the value of L is equal to 2 Henry. So, L into C is nothing but 2 into 2 is equal to 4 here. So, or putting the values, it will be d2v plus dt2 plus 1 by 4 into v is equal to, if any mistake point out. So, this will be the thing. This is the differential equation. So, I rewrite this differential equation as d2v dt2 plus 1 by 4 v is equal to 0. Okay. Then what I have to do? I have to form the characteristic equation. What is the characteristic equation? M square plus 1 by 4 is equal to 0. What will be the roots? M1, M2 will be equal to, see, I will write like this, it is equal to m square is equal to minus 1 by 4. Therefore, if you take square root of both the sides, m1, m2 will be equal to plus minus j by 2, where j is root over minus 1. Complex imaginary number j, and this becomes up. So, once are the roots are distinct? Yes, they are not equal, because one is j by 2, another is minus j by 2. Therefore, the solution V t I will write straight away. It will be equal to a into e to the power j half m1 into t plus b into e to the power minus j half into t plus forcing function is 0. So, this term x, x dots, these are zeros, nothing is there, is not? This will be the thing. Now, if you look at the boundary conditions, I told you that this is the capacitor, this is V t, and this is I, current flowing through the inductor, and I told you V 0 minus is equal to 0, no 0, 10 volt. In the previous slide, most probably I told 10 volt. No, I have not specified here, and I 0 minus is 0, and I 0 minus is 0. Do not forget to write down the units, 10 volt and 0 ampere. This was the situation. But you see, it is a second order differential equation. How many boundary conditions I will demand? I will demand that give me the value of V 0 minus, that is there, and also give me the value of dV dt at 0 minus. And these are nothing but I will demand V 0 and dV dt 0. You have understood this point, hopefully. See, after you have closed the switch, in no time 0 minus to 0, voltage across the capacitor cannot change instantaneously. So, I will say boundary conditions are V 0 is equal to 10 volt, that is one boundary condition. Capacitor voltage cannot change instantaneously. Similarly, the current through the inductor this current, mind you, this is the direction of the current, I 0 must remain 0. These are the two boundary conditions. Therefore, the first boundary condition will give you, if you put t equal to 0, V 0 is equal to 10 volt, will give you A plus B on the right hand side, T 0 is equal to 10 volt. This is equation 1, important equation, because constants are to be determined. Here is, of course, there is no terms involving forcing function. So, this is A and B are to be found out. Now, the second boundary condition is dVdt. How do I get that? I have already told you the current in the circuit I t is equal to minus C dVdt. That is what we got. C is how much? 2 farad. So, C minus 2 dVdt. This is the expression of the current. So, this current has to be 0, I 0 is equal to 0 implies that dVdt must be equal to 0 at t equal to 0, these two conditions. Therefore, to get the other equations, what you do is you differentiate this dVdt. See, C does not come into dVdt, because 0 on the right hand side. Therefore, this if you differentiate both the sides, now dVdt, it will be differentiation of this, that is j by 2 into A into e to the power j t by 2, is not this term, minus j by 2, this constant will come out, into B was there already, into the e to the power minus j t by 2. That will be the thing. And I am telling dVdt at t equal to 0 is 0. So, dVdt at t equal to 0 will be, put t equal to 0 there. So, j by 2 into A minus j by 2 into B, t 0, these are 1 and this is 0, I am telling, it has to be. Therefore, you get A minus B is equal to 0, if any mistake point out. Na? So, this is the thing, this is the other equation. So, you have got these two equations. Therefore, add these two equations, from these two equations you will get A is equal to 5 and B is equal to also 5, because A equal to B. So, these are the two constants you have get and you have almost solved the problem. Therefore, I will say voltage across the plate of the capacitor V t will be equal to A into e to the power j by 2 into t plus 5 into e to the power minus j by 2 into t. This will be the solution, hopefully correctly written. Now, this is the thing, j is root over minus 1, imaginary purely. Now, these two things can be combined together, j t by 2 plus e to the power minus j t by 2. You must be remembering that e to the power j theta plus e to the power minus j theta will be equal to 2 cos theta. Is not because e to the power j theta is equal to cos theta plus j sin theta, and e to the power minus j theta is equal to cos theta minus j sin theta. We will be often using this. So, I hope you know this complex algebra. So, this then will become e to the power j theta is this. So, if you add these to 2 cos theta you will get. So, 5 into 2 cos t by 2, which will be equal to 10 cosine t by 2. So, voltage across the plate of the capacitor is equal to 10 cosine t by 2. So, we have got the voltage across the plate of the capacitor. And the expression of the current, and what the point I want to make, see, although in the expression, and there is no solution due to forcing function, no forcing function was there. See, the capacitor was charged with a real number plus minus 10 volt, then initial voltage, this is initial voltage. At any time the voltage is V t, and this is L. This is L, and this is your I t. Now, we see in this circuit, therefore, at the end the voltage, current, whatever you solve for, they should be real. Why they should be imaginary? In fact, this complex numbers will never betray you in that way. But I have followed strictly the rules. Roots are separate, distinct, although they are imaginary, but we know that it will, I can write down the solution just by inspection. That is what I did. Then I applied the boundary conditions to get the constants here A, B, and I followed strictly the rules and got this as my voltage. What will be the current? Okay, one can form a differential equation involving current and solve it. That I am not going to do, because once I have got the time domain expression for the capacitor voltage, I t I know it is equal to minus C dV dt, is not? That is what I got. So, minus C means minus 2, capacitance is C, I have assumed, and d dt of 10 cosine t by 2, which if you differentiate cosine t, negative will come, this negative will make it plus. So, it will be 20 into sine t by 2 into half, that is 10 sine t by 2. So, we write I t is equal to 10 sine t by 2. See, just application of the rules I have derived. I have never multiplied with multiplying factor, integrating factor, this, that are things of the past now. After I have learned how to solve a differential equation, you can analyze the circuit and find out the characteristic roots, forcing function, in this case it was like that. So, if I now sketch these two things, what will be the nature of the solution? So, I want to sketch capacitor voltage Vt and the current in the circuit It. At t equal to 0, I did the switching, t equal to 0, t equal to 0, I did the switching. See, the capacitor voltage was 10 volt earlier, suppose it is 10 volt, suppose this is 10 volt. Then it changes with respect to as a cosine function. So, the nature of solution of capacitor voltage will be something like this, is it? Zero crossing points can also be found out, because cosine pi by 2 it will be 0. So, t by 2 is equal to pi by 2. So, t is equal to pi, this point will be pi, and so on. You can mark this point. This is time, mind you, not theta. So, this is pi, correct. Now, the interesting points is, and this peak value is 10 volt. So, capacitor voltage will oscillate like that. What will be the frequency of oscillation? This omega of this thing, omega t, omega is half, so much radian per second, is not sin omega t, omega is half. What is the time period? What will be the time period? That is this time. Two pi by omega, 2 pi by omega, which is equal to 4 pi in this case. So, this is equal to 4 pi for this problem. So, okay, this is the time period that I have got. Now, let us, so capacitor voltage V 0 minus was 0. Then from that it started oscillating sinusoidally, co-sinusoidally like this. What about current? Current, if you see, it is a sine function, sine t by 2. So, current waveform will be like this. If you sketch it, this is IT. What is this IT? 10 sine t by 2. So, this one is 10 ampere, this one is 10 volt. It will be varying sinusoidally. Got the point? And then it will be like this. And it will go on doing like this. Therefore, a capacitor and inductor, which are ideal in nature, no resistance involved, if you charge the capacitor from some other circuit to 10 volt and then switch on to an inductor which had got no initial current, then you see the voltage across the inductor or across the capacitor and the current in the circuit will be oscillating, changing with time indefinitely. There is no decay. Why? Because there are two energy storing elements, several things we will say. That is why you got a second order differential equations, and then voltage and current will oscillate. What is the value of omega? Omega value is 1 over root over L C. Omega value you can easily see. This omega value, L and C were 2 each. So, this omega is also equal to 1 over root over L C. You can easily show that. Anyway, it will do like that. So, you started this circuit with no external source connected. You had a capacitor where energy was stored. How much was the energy? Half C into V naught square, initial energy stored. Stored in C. What was the initial energy stored in inductor? 0. You started with that. Initial energy stored in L was 0, because I was 0 at that time. Initial means t equal to 0, implies t equal to 0, like that. Now, you see, as we have connected, let us now try to see the physical thing, what is happening. Okay, equations are fine, you have got the solution. Initially, you started with this much energy. How much it was? Half, this one, half, C was 2 and this was 100, 10 square, that is 100 joules. You started with 100 joules. There is no energy storing, energy dissipating element, no resistance in the circuit. So, capacitors start discharging energy, losing voltage means capacitor energy is decreasing. A time will come at t equal to pi second, capacitor voltage will collapse to 0 at that instant, and at that instant the current through the inductor will be 10 ampere maximum. At t equal to pi, at t equal to pi second, capacitor stored energy in capacitor, capacitor energy is half C 0 square, that is 0, 0 square, 0. Energy stored, energy of inductor at t equal to pi second will be equal to half L into I square, I is also 10 ampere into 100 is equal to 100 joule. That means, capacitor started losing energy and inductor was gaining energy. When capacitor energy was 0, inductor, that is why the 0 crossing of the capacitor voltage will give, always tell you that current in the circuit is maximum, that is here also, here this maximum current, plus 10 minus 10 squared, if you make it is plus. So, this is also minus 10 ampere, 10 ampere, it will be like this. So, this is how things will continue forever. It is a very interesting circuit used called tank circuit, it will start oscillating, you start with that. What about at any time t? At any time t, energy stored in inductor is half L I square, energy stored in the capacitor is half C V square. L and C are 2, so this is equal to I square plus V square for this problem, C equal to 2, L equal to 2. What is I square? I square is 10 square sin square t by 2 plus 10 square cosine square t by 2, and that will be equal to always 100 joule. That is this, you started with 100 joule, 100 joule, no one is there to dissipate that energy. So, energy capacitor will charge the inductor to its maximum current, then inductor will start discharging when the current becomes negative and capacitor will charge up. That is one thing. And another thing I would like to tell you that you see between 0 to pi, if you are really following me, I will appreciate if you also try to understand this point. See, voltage across the capacitor during 0 to t pi, 0 to t, this pi is second, 0 to this second, 0 to pi second, voltage applied across the inductor was positive and current must go on rise. That is what exactly happened. You spend this much volt second to charge the inductor here, and current rose from 0 to 10 ampere, positive volt second you have spent. This is also pi, na, 2 pi it will be, is not pi to pi. During this next pi second, you have applied negative voltage. So, di dt has to be negative. So, current has started decreasing. Voltage applied is this negative voltage across the inductor. Therefore, current wherever it rose to 10 ampere, from that it must start decreasing. And during this pi interval, you have applied a negative volt second, and these two are same. This, if you integrate this volt second and that volt second, this is same. That is why current rose to 10 ampere, but once again came to 0 ampere. From this to this interval, this is 3 pi. Na? From this pi interval, what you are doing? We are still applying negative voltage. Therefore, di dt must be negative, and it will continue like this. So, negative volt second you are applying during this interval, so that current becomes minus 10 ampere, and eventually these two areas are same and current will once again come to 0. So, this is a rather simple circuit, but nonetheless it will always think behind all these mathematical steps that I have done, physically try to understand what is happening. All the concepts of volts again. Similarly, you see the capacitor voltage, it is decreasing here. Why it is decreasing? Capacitor voltage? Because you are draining out current. This IT, mind you, is drained out, is not, from the positive plate. So, capacitor voltage, you have essentially applied a negative current to the minus IT will be like that. So, think in those terms, and we will consider several. We have now made enough background to analyze any circuit. Now, I am telling, I will not put any restriction to the voltage, let it be DC voltage only. No, I will take any time varying voltage. I will also not use only resistance in the circuit. In fact, in practical circuits, there will be inductance capacitances present. So, most general and with initial conditions also. So, your excitation may be time varying, your response may be time varying, all the restrictions are gone, and this will be the most general differential equation you will write down for the system in the form of KVL, KCL, and then try to solve the differential equation, and at this stage solve it classically the way I told you. Then at later stage we will also tell you the use of Laplace transform, which is also a very elegant method, but this approach of solving the differential equations classically gives you more insight into the problem. At every step you can check, oh, this is how it looks like. So, make habit of sketching waveforms of voltage current in a time varying environment and try to interpret the results. Thank you.